Hello and welcome to EngPhys 3 BA3 Lecture 7, where we're going to be talking about transistors for the first time. Transistors are the first three terminal devices that we're getting to in this course. There's generally a control terminal and then the main conduction path terminal. So this is a BJT transistor. For a BJT, we call the control terminal the base, and we have the two other terminals are the collector and the emitter. So the base voltage determines how easy it is for current to flow from collector to emitter, or vice versa. So how difficult it is for current to flow between these. Let's look at the band diagrams and how you would actually build a transistor. An NPN transistor has an N-doped region. Here's a picture of how you'd actually build it, N-doped region, then a P-doped region for the base, and an N-doped region for the collector. The circuit symbol for NPN looks like this. And how does this work in band diagrams? In the usual operating case, you would put higher voltage on the collector than you put on the emitter. So in band diagrams, we are plotting the potential energy for electrons. So higher voltage on the collector means it's at a lower potential energy. Okay, now if we were to apply a voltage at the base relative to the emitter, so a higher voltage at the base than the emitter, but not as high as the collector, then what's going on is we are lowering the barrier for electrons to jump from emitter over to collector. So because we've got lower potential energy over here, electrons are going to want to jump from the emitter through this base region where they're the minority carrier over to the collector. But they can't unless we apply a voltage to forward bias this junction. So by applying a positive voltage at the base relative to the emitter, you see we're going to be lowering this barrier and have electrons jump over. This is a picture of what it looks like in the normal or active mode of a transistor, where electrons can actually flow across from emitter to collector. The current flow is the opposite of that, and the arrow shows the direction of current flow. In addition to an NPN transistor, we also have a PNP transistor, and in that case, the current directions are the opposite, and so are the bias voltages that you would need to make this transistor operate. So the base collector junction is reverse biased, and the voltage there is whatever it needs to be, because there's no current really going from between collector and base. We're going to ignore any current that's going actually out of the base terminal. So all of the current goes almost entirely from collector to emitter in the normal operating region. The emitter is called the emitter because it emits the majority charge carrier. So for an NPN transistor, that means it's emitting electrons. So the collector current plus the base current is equal to the emitter current in either device. Just in an NPN transistor, we've got the collector and base current going into the transistor and the emitter current coming out, while for a PNP, it's the opposite. The emitter goes in and the base and collector comes out. Either way, the emitter is equal to the base current plus the collector current, and in the usual operating mode, the collector current is many times bigger than the base current. It's larger by a factor beta, so the collector current equals beta times the base current. Beta depends on which point of the transistor we're operating it at, and typical values for beta are 20 to 400, so it can be quite large. All right, we've got a model for how the transistor is going to behave called the Ebers-Moll model, or Ebers-Moll model, however you want to say that. I'm not really going to be picky about that. So let's say Ebers-Moll model, we've got base current is equal to this collection of diode effects. So we've got a base emitter diode and we've got a base collector diode, because it is still a diode from base to collector, and if we were to apply any arbitrary voltage, then you could see why the base current may depend on both of those junctions. And adding those up together, the ones cancel, so we end up with this. This assumes that the reverse bias saturation current for each of the diodes is the same, and so really it would only approximate to this for a symmetric BJT. And the collector current, similarly, we can write in terms of diode currents, but most of the time we're just going to say, well, in a typical situation, the collector voltage is larger than the base voltage, VBC, so the voltage of the base relative to the collector is negative. This is all for an NPN, by the way. For a PNP, you would just reverse all of the voltage signs. The terms proportional to VBC in the two equations are much less than the other terms because this is a reverse bias diode. So once again, the collector base diode is reverse biased. So again, we put positive voltage on the collector, then more negative on the base, and the most negative on the emitter for an NPN, which means that the base emitter junction is forward biased, but the base collector junction is reverse biased. Okay, so that means that the base collector voltages that appear in these equations are negligible compared to the base emitter terms. We've got reverse bias diodes having much less current than forward bias diodes. So effectively, you can say that the collector current is basically just equal to this diode equation IS e to the E. So the E in the exponent here is the charge of an electron, VBE by KBT minus 1, and the base current is equal to the collector current divided by beta. That's just a rearrangement of IC is beta IB. So to summarize the previous information into some more heuristics, things that we're going to use to talk about transistors most of the time. Normal operation is when the collector voltage is bigger than the emitter voltage. This is what makes the potential energy for electrons lower on the collector side, so that electrons are going to want to flow from emitter to collector and not the other way around. Then, in addition to normal operation, we can talk about a subset of that called active mode, which is where the collector voltage is higher than the base voltage on top of that. So VCE, collector relative to emitter, is bigger than the voltage of the base relative to the emitter. This is all again for an NPN. If we were talking about a PNP, we would reverse that. So in this situation, then the collector current is actually independent of the collector emitter voltage drop. Well, not quite. We'll look at some curves that explain, that show some deviations from that. But it's basically independent of that and depends mostly on the base emitter voltage. You'll notice that in this diode equation, it looks almost like a diode equation, except it kind of depends on the wrong voltage, right? So this is the collector current, but it depends on the base voltage, the voltage of the base relative to the emitter. Coming back up here, we've got the current going in the top here, depends on the bias voltage of this junction down here. And again, that's because the collector is lower potential energy. So you can think of it as the amount of electrons that we get flowing from emitter into the base depends on the base emitter voltage. And then once those electrons are up there, though, they don't actually exit the base because they go, whoa, look at this potential energy drop over there. So they all fly over to the collector side and exit that way. So the collector current depends on the base emitter voltage because of that. If the voltage drop between the base and emitter exceeds the voltage threshold, the base current will jump up exponentially, of course, because the base emitter is just a diode. So you have to be careful not to just try to apply some massive voltage between base and emitter in order to get your collector current to fly up a lot. That's just going to be sinking too much power into the transistor. It is just a diode from base to emitter. Current's always conserved, so we define the emitter current as the base current plus the collector current using our directions. So for an NPN, emitter current is defined as going out of the transistor, and these two, base and collector, are defined as going in. Saturation mode is the mutually exclusive mode to active mode. So as long as you're in normal operation anyway, you can be in either active mode or saturation mode. Saturation mode is when you've applied so much base emitter voltage that the collector current doesn't keep rising up anymore like you'd predict from here. So when VBE is increased, eventually the electron barrier is so low, the current from collector to emitter is controlled by the external load resistance. Going to this picture, you can see that if we were to try to drop this, as long as once the base voltage is high enough so that this potential energy barrier is not a barrier at all, then the amount of conduction isn't going to depend on that voltage anymore, and it's going to depend more on the other things that are in place in the circuit. So what's going on outside in the collector's load line, essentially. Okay, and that's the saturation mode. Exercise 5.2. An NPN transistor has a 100 ohm resistor connected from its emitter to ground, and its collector is connected directly to a 10-volt supply. The base voltage is set to 1.5 volts, and we're given that beta is equal to 200. Beta is, again, the collector current divided by the base current. Since VCE, the voltage of the collector relative to emitter, is greater than voltage of base relative to emitter, the transistor is in active mode. Determine all the currents going into and out of the transistor using the approximate rules, and then using the approximate Ebers-Moll equations. For those ones, we're going to be given the transistor parameters IS and kBT over E. Okay, so the approximate rules say, well, this is just a forward bias diode, so the drop is 0.6, which means there's 0.9 volts there, and you can say what the current is across the through this resistor here. So the current through that resistor, the emitter current, is approximately equal to the collector current because beta is large. So that tells us what the collector current is as well, and then we just divide the collector current by beta to get the base current. Let's look at that. With the voltage of the base set to 1.5, we've got VE is equal to 1.5 minus VBE from Kirchhoff's laws. And we say, well, VBE, since it's a forward bias diode, is approximately 0.6. So this gives us 0.9. So the current going through the resistor is 9 milliamps. Assuming that IC is 9 milliamps, IB is equal to IC over beta is 45 microamps. Now you may be wondering, all right, we just said the emitter current is equal to the collector current. Why is that a good approximation? Well, because beta is so big, almost all of the current going out of the emitter is from the collector, not from the base. The collector current is 200 times bigger. So this is only a 0.5% error to just say that the emitter current is equal to the collector current, and it lets us solve things a little bit quicker. It's not that big of a time saver if we were to just write this as IC plus IB over beta is equal to 9 milliamps, and then solve for beta, or solve this equation for the collector and base currents using that. All right, so the Ebers-Moll equations, what does this get us beyond doing that? The only advantage of the Ebers-Moll equations is it says, well, you know, the base voltage, base emitter voltage, we said that's approximately 0.6. It's probably not really 0.6. So let's figure out what it would actually be by setting up some equations. So this is going to be basically like we're doing with the diode and load line there. So we'll say that we've got a VBE, and we don't know exactly what it is. And the VBE is going to determine the collector current. Now, once we've got that collector current, we can relate that back to the base current through beta. And so let's come up with the equations we've got. We've got that the collector current plus the base current is the emitter current. And we know the emitter current is 1.5 minus VBE over R1. That's the load line on the emitter side of things. And since we know that the collector current is equal to this diode term that depends on the base emitter voltage, we've got a usual diode looking thing that we can solve for the base emitter voltage. The only difference is that in front of it we've got this 1 plus 1 over beta term that showed up because it's the collector current plus the base current there. Okay, so you can solve this iteratively or with Maple or however you like and find out what the actual base emitter voltage is, and I get 0.57. So that means that the currents were slightly different than we predicted with the approximate model, but not too different. So the approximate solution is a pretty good thing to do. Characteristic IV curves. Now let's look at how transistors actually are operating. Even the Ebers-Moll model is an approximation. So we said that as we increase the collector emitter voltage, as long as we're in the active region, the collector current doesn't change. So these curves are horizontal, the curves along the back here. Ignore the load line for now. So, but they're not quite horizontal, right? So you can see as we get to this higher base current, that's what we're showing on the different labels of the curves, we have a a larger amount of collector current. So increasing the base current increases the collector current, but the collector current also does depend on the collector voltage. So first of all, we have to be in the active mode in the first place. If we're not in the active mode, if we don't have enough collector emitter voltage, then the collector current goes way down, and that's this saturation mode we were talking about on the left. You can see, so earlier we described it as if you apply too much base voltage, then we go over into the saturation mode. How the collector actually behaves is kind of a compromise between the transistor parameters in the back and the circuit that it finds itself in, which is going to determine this load line. So that's the load line here is the collector terminal load line. So it depends on, it's a relation between collector current and collector emitter voltage. And the slope of this is going to be determined by what resistor you've got on the collector side of things. So as we try to increase the base voltage, we increase the base current, and increasing the base current makes us move to a new curve in the background's intersection with the load line. So you see we kind of jump down and keep getting less collector emitter voltage, because as we have more current going through there, we'd have more of a voltage drop across that collector resistor. So we start moving up and up and up to the left until we reach the saturation mode. And that's why increasing the base voltage, or really the base current, is going to push you towards the saturation mode and out of this active mode region where the collector emitter voltage doesn't increase the current in the collector very much. How would you get these curves? You'd have to either find them experimentally, or you'd have to get them from a data sheet of your particular transistor if you're lucky. Where is the beta parameter? The beta parameter is the ratio, again, between the collector current and the base current. So you can find out where that is in a particular spot here by looking at the base current that we've got and the collector current that we've got. So beta, IC over IB, is also equal to the rate of change of the collector current with respect to the base current. So we're going to look at an exercise where we figure that out by looking at one of these plots. And we'll find that if you were to do this for different points on the plot, you'd find that beta isn't really a constant. And that's why if you want to get an exact answer, even the Ebers-Moll model is not good enough, and you've got to go back to these curves here. Now, how do we get the base current in the first place? Well, that one, we're just going to be using a regular diode equation at the base. So we'll figure out what the base emitter voltage is, and we'll use the load line for the base circuit to figure out what voltage drop we've got there. In the previous example, we have a resistor on the emitter side of things, and that means that we can, this is a little bit easier to analyze than if we have a separate load line for the base and the collector by having different voltages on different resistors on each of them. Okay, so let's look at this other case. Now we've got different resistors on the base and collector. So the load line for the collector is determined by this RL, and the load line for the base is determined by the resistance in the base. Normally you want the base current to not be too big, so you'd want this R to be usually quite a lot larger than this resistance. Or if you've got, that's if your input voltage is anywhere close to Vs. You could also make the base current smaller by just having Vi be quite a lot smaller than Vs. All right, so the operating regions, just to summarize that, we've got the forward active region, what we've just been calling the active region, and then the saturation region if you increase the base voltage too much to the point where the collector current is not just a constant with collector emitter voltage. Now, you could also just reverse all of the flows and get current flowing in the opposite direction. So if we have, say, the emitter voltage higher than the collector, you could get electrons to flow in the opposite direction, because then we've just got we have sort of the same situation. But because the transistor is not exactly symmetric, it doesn't work quite as well in the reverse region. So you typically get get worse gain over there than you do in the forward active region. So it's not a good idea to use the transistor over there. Now, the opposite regions are called cutoff. So this is where you can imagine for the collector emitter voltage we've got too low of a base current, so that we don't get any collector current. Now, if you were to make this plot again, but instead of plotting base current in the background and then collector emitter voltage and collector current, you were to just plot the two voltages, you can reimagine the two regions. So the saturation region is when we've got large enough VBE and very large base voltage relative to the collector. So the base is higher than the collector. The normal forward active region is when the collector voltage is higher than the base, so we'd be down here. As long as the base emitter junction is forward biased, then we're either in forward active or saturation. If the base emitter junction is not forward biased, then we're either in cutoff, or if we were to also have the base be higher than the collector, we can get into this reverse active region. So just be aware of that. Exercise 5.3. For the characteristic curves shown in figure 5.8, estimate the gain beta of the transistor in active mode. So as long as we're in this region over here, find the gain beta of the transistor. All right, well, we know that beta is the rate of change of the collector current with respect to the base current. So you can just read this off the plot. Let's say IB is 10 microamps, and the change in IC, by looking at from 10 up to 20, you can read off on the left, we've got a change in IC of 0.002 amps. So a 10 microamp change in the base current gives us a 2 milliamp change in the collector current. So 2 milliamps over 10 microamps, about 200 is the beta. If you were to do this really carefully on different parts of the curve, of the graph, you'd probably find differences in what beta is. And that's why you really need these curves. You can't just say beta is a constant. Certainly in the saturation mode, it doesn't work like that. And even over here in the active mode, beta is not exactly a constant. Exercise 5.4, we're given this circuit, and we're given this set of characteristics for the transistor in the back, the characteristic curves, collector current versus collector emitter voltage, and we're also given this load line for the collector side of things. But what we're not told is what VS is or RL is. So if part A says for this load line, find the supply voltage and the load resistance. Okay, so what you should do is first write out the load line equation using variable VS and RL. And then using that equation and this graph, you can pick off what your VS and RL are. Okay, load line equation is the collector current is equal to the drop across this resistor divided by that resistance. And looking at this equation, you can see, well, we'll get 0 collector current when VCE is equal to VS. From the plot, that's when VCE is 14, so VS must be 14. Now, we'll have, on the other side of it, we'll have 0, when we have 0 collector emitter voltage, that's when we get the maximum collector current, and that would be VS over RL. So since VS we figured out is 14, and IC in that case is 10 milliamps, we can solve for RL, 14 over 10 milliamps, 1400 ohms. That's part A. Part B, for those values we found, determine the operating voltage drop, VCE, for a base current of 10 microamps. And we're going to figure this out two ways. One, just by reading it off the plot, and two, using the Ebers-Moll equations to simulate the IV curve with those parameters that were given. So reading it off the plot, if beta is, or rather not beta, but IB is 10 microamps, then VCE is the intersection of the load line and the characteristic curve for 10 microamps, 12 volts. That's it. Now, Ebers-Moll model is both more difficult and less accurate, but it doesn't require you to have these curves. So let's give that a shot. Ebers mole is IC is equal to this combination of diodes, which for large VCE compared to VBE means that the reverse bias diodes we can just neglect from the equation and say, well, it's approximately IS over beta e to the e VBE divided by KBT. Let's check out what base voltage we get to see if that was justified, that our VCE, which we are guessing is pretty big, is going to be much larger than VBE. So by solving that, by rearranging this in terms of VBE as a function of IB, which in this case we know is 10 microamps, we can substitute everything in and find out VBE is actually 0.18 volt, quite a lot smaller than the VCE that we're predicting, around 12 volts. Okay, now let's find out what VCE we actually get in this situation by writing out our Ebers mole collector side of things. So the Ebers mole collector current up here must be equal to the load line collector current. But again, since VBE is small, we're just going to ignore the reverse bias diodes and say the collector current's approximately just IS e to the Q VBE divided by KBT. So solving this equals that for VCE, which doesn't really require complicated or iterative solutions, because this is the base emitter voltage. You can either sub in the base emitter voltage or just say, well, this is beta IB. Then using our load line, we find VCE is 12 again. Okay, one more part to this question. Plot the IC as a function of VBE predicted by Ebers mole with these parameters for a few choices of the base current, and compare how it simulates the measured curves to the actual measured curves. What are the big differences? We didn't really need a lot of the math here for how we ended up solving the collector emitter voltage. I mean, if you look at this, we just used the beta. We didn't use any of those other internal parameters. Those were just used to figure out what the base emitter voltage was. For part C, though, we're going to solve this for a variable base current and plot some and create some plots, so we do need the entire model. If you do that, you come up with these curves. And this explains what's going on with the Ebers mole model. It makes the approximation that the collector current doesn't depend on the collector emitter voltage as long as we are in the saturation region, rather the active region. Saturation region is the one over here. As long as we're in the active region, the collector current doesn't depend on the collector emitter voltage. In reality, we know that that's not quite true. It does rise a little bit with collector emitter voltage, even in the active region. And that's it for today. We'll continue with section 5.3 in lecture 8.